Tensor analysis is the foundation of relativity, actually. I have here two textbooks on tensor analysis, actually. The first one is by Bishop and Goldberg, Tensor Analysis on Manifolds. And the other one is Tensor Analysis by Sokolnikov. What is it? Okay, I don't know what it is. Actually, I bought this book recently, well, a couple of years ago, well, 3 years ago, actually. I was teaching in the UAE, and then I came across this textbook somehow online. Let me show you here the table of contents for this book. So here we have the contents table down here, linear vector spaces, matrices, coordinate systems down here, the summation convention, chapter number 2, transformation of coordinates, properties, the tensor concept. Let me show you. Let's move on to chapter number 3, the geometry. Okay, so some applications here to geometry. The length of an arc, non-Euclidean geometries down here, curvilinear coordinates, the Riemann-Christoffel tensor in the Gaussian curvature down there. And then chapter 4, analytical mechanics. So this is an application actually to mechanics down here. Newton's laws, dynamics, Lagrange equations, Hamilton's principle. So it's a super, like, if you will, physics geared textbook, actually. Some applications here to relativity as well. Okay, Einstein's gravitational equations, relativistic mechanics, Newtonian mechanics, and stuff like that. Honestly, I have no idea about these topics. All right, I wanted to learn about tensor analysis, but for some reason, I never had the chance to grab the book and have a look at it. But then yesterday, guys, I came across this book down here, Tensor Analysis on Manifolds by Bishop and Goldberg. And this is a totally different approach from the one we have here in the book by Sokolnikov. So let's have a look at it. I don't remember when I purchased this book, actually. So it's been there in, with a bunch of books there, but I never had the chance to scroll through the textbook itself, and I did it yesterday, and I found it's amazing. Look, let me tell you, they start out by talking about the set theory. So set operations, functions, and set operations. Then they move on to topologies, metric spaces, subspaces, continuity, the concept of continuity in this context, connectedness, compactness. Then they move on to the concept and definition of manifolds. So definition of a manifold, plenty of examples of manifolds down here because I checked the textbook, differentiable maps, submanifolds, tangent spaces down here, coordinate vector fields, the differential of a map, and then tensor algebra. They do that in chapter number 2. So they develop here basically the theory of tensors and the algebra of tensors, along with the theory of bilinear forms. Chapter 3, vector analysis of manifolds. Amazing. Look at this. Concept of the vector field actually flows, the Lie derivative down here. I was checking actually in this chapter let me see if I can show you quickly. I came, oh, here it is. Look, page number 151. They developed the concept of a distribution. Now, the distribution in the sense of differential equations, right, has nothing to do with the concept of the formal distribution as generalized functions, developed that the Schwartz distribution. A distribution is just a subset of the tangent space at a certain point of a manifold, okay, of an abstract manifold, such that the bracket actually leaves that subset invariant. That's a distribution, grosso modo, okay, in a few words. The concept of the distribution, it's extremely important in differential equations, actually. And actually, what's important is the so-called Frobenius theorem, okay? It's right here, Frobenius theorem. There. 3.12.1. A C-infinity involutive distribution is completely integrable. If you have the chance later to learn a little more about foliation theory, you will realize it's a beautiful topic in mathematics because it's related to partial differential equations, dynamical systems, and geometry. Sometimes complex geometry as well. And then chapter number 4, integration theory. So how to integrate differential forms, actually. All right. Chapter 5, Riemannian and semi-Riemannian manifolds down here. Flat spaces, parallel translation, covariant differentiation, curvature and torsion, tensors down here, geodesics. It's a nice addition to your collection. Tensor analysis on manifolds by Bishop and Goldberg. There you have it. Thanks for watching and see you in the next one.